Alright, so today I'm gonna be explaining this important paper with the title NCGNN, Node Level Capsule Graph Neural Network for Semi-Supervised Classification. This IEEE paper in 2022. Message passing has evolved as an effective tool for designing graph neural networks. However, most existing methods for message passing simply sum or average all the neighboring features to update node representations. They are restricted by two problems: lack of interpretability to identify node features significant to prediction of GNNs, and feature over-mixing that leads to over-smoothing issue in capturing long-range dependencies and inability to handle graphs under heterophily or low homophily. So they propose a node-level capsule graph neural network to address these problems with an improved message passing scheme. So NCGNN represents nodes as groups of node-level capsules, in which each capsule extracts distinctive features of its corresponding node. For each node-level capsule, a novel dynamic routing procedure is developed to adaptively select appropriate capsules for aggregation from a subgraph identified by the designed graph filter. So it aggregates only the advantageous capsules and returns irrelevant messages to avoid overmixing features of interacting nodes. Therefore, it can relieve over-smoothing issue and learn effective node representations over a graph with homophily or heterophily. Then their proposed message passing scheme is inherently interpretable and exempt from complex post hoc explanations, as a graph filter and a dynamic routing procedure identify a subset of node features that are most significant to the model prediction from the extracted subgraph. You see the comparison of different message passing schemes from node X to node Y. Each cubic is a scalar, while each capsule is a vector. So in A, you see the vanilla sum aggregator that we always do, but in B, you see the multi-channel message passing scheme with 4 sum aggregators. And in C, you see the dynamic routing procedure between node-level capsules. Inspired by the interpretability and dynamic routing procedure of capsule networks, several capsule-related GNNs have been developed in the graph domain. However, they commonly focus on graph-level classification, or flatten the capsules back to conventional scalar features. So we propose node-level capsule. So this is how we do message passing. And as I said, figure 1 is a brief comparison of different message passings. So we have a measure for homophily ratio. So we categorize the graphs into associative and disassociative ones according to homophily and heterophily. Associative graphs are those with high homophily ratio. For example, this is closer to 1. This value, h of g, is closer to 1. When we have a citation network, social network, some of them. On the other hand, disassociative graph exhibits heterophily or low homophily, which is closer to 0 this time. For example, connections of different types of amino acids in protein structures, and web page linking networks are two typical examples of disassociative graphs. So this is the workflow of NCGNN. First, transforms each node from a scalar feature to k primary node capsules. Subsequently, the design graph filter selects a subgraph for each target node to perform message passing, and dynamic routing is leveraged to generate C-class node capsules for it. So C is a number of classes. In capsule graph layer, each node level capsule adaptively selects appropriate capsule to update its representation via dynamic routing, and irrelevant messages from neighborhoods are restrained to avoid feature overmixing. So we only plot the message passing procedure for generating class node capsules. So the capsule layers can be further stacked if necessary, though we only used one capsule graph layer to produce C-class node capsules for each target node. So after doing dynamic routing, we can have class node capsules. These are primary node capsules, then we have class node capsules. But the important thing is we go from node level to capsule level by this transformation. So we elaborate the proposed method. We have two research questions. For each target node, how to identify the graph nodes whose information should be aggregated. The second question is, for each target node level capsule, how to determine and aggregate an appropriate subset of capsules that contains little noise from the subgraph. So for question 1, by selecting a subgraph for each target node with two graph filters designed in the attention and diffusion-based manner. And for question 2, by designing a capsule graph layer where message passing is improved with a novel neighborhood routing by agreement mechanism between node level capsules. So first, convert each node from scalar level feature to a group of primary node capsules by projecting the node features into k different subspaces. So this k varies from 1 to So this k varies from 1 to k. And the denominator is just a Euclidean norm of that. For each target node, the graph filter identifies a subgraph where information should be aggregated and determines the influence of each subgraph node on it. So this is the generalized filter. And this f of kc is a polynomial function. So this exponentiation operation of a tilde may result in a dense matrix even for small I. So each row of A bar, each row of this identifies part of the n nodes or subgraph for the corresponding node to aggregate information, and each non-zero entry denotes the influence of message passing between two interacting nodes. And then this is the attention-based graph filter and diffusion-based graph filter. The attention-based graph filter is learnable, it's flexible, there is no constraint on M. The diffusion graph filter by these advances in these propagating features like a personalized page rank, heat kernel, that is their motivation, that they create such things. So we evaluate performance of personalized page rank as the fixed diffusion based graph filter. So F sub C is the dimension of class node capsules. And this W is the learnable weight matrix between case primary node capsules and the else class node capsules. So this C is the coupling between H and P. So we want the length of the output vector of each class node capsule to indicate the presence of an instance of class L. So we use the squashing activation function in equation 10 to ensure the length of the output vector lies between 0 and 1, because that represents the probability that nodes belong to class L. So it should be between 0 and 1. And then we can calculate the loss of the else class node capsule of node V sub I. So once we have subgraph nodes and which are identified by a bar, the output is the output vectors of C-class node capsules. So we want to learn these W parameters. And they did experiments on Chameleon squirrel, which have high heterophily, very disassociative high heterophily. And they compare it. They have also assortative graphs, which is easy. And then they have average classification accuracy. For example, they compare graph attention with their method. You see, from 76 we go to 79 for Cora dataset. But these are simple datasets. How about Chameleon and Squirrel? For example, from graph attention, from 30 we go to 48, which is a great improvement. Or from 54 we go to 63.